Okay, this is part 2 of the October 2023 paper, Unit 4, Edexcel, International Physics A-Level. So we went through the multiple choice in the previous video. I'm now going to go through a few of the longer questions and try to keep the video to 20 minutes or less. Okay, so let's go straight into it. So section B starts always with question 11. Hopefully it's zoomed in enough for you. Let's try and zoom in a little bit more so it's easier to see the text. Okay. I've got my camera on, so hopefully it won't put you off. So the first question in the section B is about circular motion. The photograph shows children on a roundabout in a playground. When I'm answering these questions or when I'm reading them for the first time, I always do what I call active reading, which I always advise my students to do. So if you've got a pen or a highlighter in the exam, I would actually underline key words. You'll notice I've already put some notes down to make sure that I don't forget to give you the information you need. Okay, so the roundabout is a flat platform with bars. The diagram shows you the bars and the platform. The children make the platform rotate by running on the ground whilst pushing the bars. Okay, it takes 12 seconds for the roundabout to make 2 complete rotations. So it takes 12 seconds. I don't know if you can see the highlighter. The highlighter's probably not as visible as I would like. It takes 12 seconds for the roundabout to make 2 complete rotations. So that allows us to work out period or frequency. Okay? So it's just like we know it takes 12 seconds, so frequency is how many per second, and period is the time for 1 complete rotation. So that already we know how to do that. So we'll carry on reading first. A child is standing on the platform, 1.8 meters from the center of the roundabout. So that's telling us that R is 1.8 meters for the girl. And then it tells us that they want us to calculate the speed of the child. So they want us to calculate the speed of the child, v. So what equations do we need to use? Okay, so to work out the speed of the child, we would need to use v equals r omega in rotational mechanics. Okay, we already know that the period, is t is going to be 6 seconds. So as long as you show that you've worked out that the period is 6 seconds, you probably get one of the marks for that. Okay? Then once we want to get v equals r omega, we don't know what omega is. So the other thing we need to use is omega is 2 pi over t. Okay? So once you know omega is 2 pi over t, that's the first thing you need to work out. We worked out that t equals 6 seconds, and you don't actually get a mark for that, but once you need that to put it into this equation. So it's 2 pi divided by 6, and you'll need to calculate that, where it's about 6 over 6. It should be slightly over 1 second if you actually calculate it, which I did before. It's about 1.505 radians per second. Don't forget to include the units in these interim calculations. So I would say, if you've got that, they will get your first mark in the question. Once you know omega, you can then use it into the v equals r omega question. We've been given r, so you now multiply the radius that you're given, which is 1.8 meters, by the omega that we just calculated, which is 1.05. So the answer will be 1.8 times 1.05, which is approximately 1.2 0.89 meters per second. Okay, so that's the speed of the child. Yeah, in the exam you should really put your answer here. But so you'll get 1 for using V equals knowing that you're having to use V equals R omega, and 1 for getting the answer with the units. Many students lose marks in the exam for not including the units. Okay, the next question is only 3 marks. So the 3-mark question is about an electron, and it's telling you an electron has kinetic energy in joules of 7.2 times 10 to the minus. It's difficult to actually read that, so let's just zoom in a bit more. (10 to the minus 16, I think it says. Yes, as you can see from my appearance, I wear glasses. So, yes, it gets a little bit fuzzy, but let's see if we can get it to focus a bit better. Anyway, it is 7.2 times 10 to the minus 6. So calculate the de Broglie wavelength, de Broglie, but I think it's pronounced de Broglie. So the de Broglie wavelength, lambda, is given by Planck's constant divided by the momentum of the electron. So they haven't given us the momentum, but they've given us the kinetic energy. Now, if you know the kinetic energy, you can either use the mass of the electron. So the kinetic energy obviously is half mv squared. Yeah? So you could work out, because you know the mass from the data sheet, you'll be able to work out the velocity and then work out the momentum. But there is a quicker way of working out the momentum, because there is an equation which is kinetic energy is equal to p squared over 2m, which is already taken into consideration the fact that you don't have to use that. So it's an algebra. This is also on a data sheet. Now we want to work out momentum, yeah, because we want to put momentum into this equation. Planck's constant is given to you in the data sheet as well. Okay, so what we want to do is work out P using this equation. So I'll just change the subject of the formula to P squared equals 2m times Ek. We know Ek from up there. So you put the values in. So P will be equal to the square root of 2 times the mass of an electron, which, if I remember correctly, is 9.11 times 10 to the minus 31 kilograms. Multiply that by the kinetic energy that we're given. The kinetic energy we're given, still having struggle reading it. Kinetic energy, I'm looking at my notes to make sure I've got the correct energy. Yes, it was 10 to the minus 16. 7.2 times 10 to the minus 16. So once you have put in the 2, the 9.11 times the mass of the, which is the mass of the electron, multiplied by the energy, you can square root it. The value for P, if you calculate it correctly, will be equal to approximately 3 significant figures. Don't put loads of significant figures down on the exam paper, because the data we're given is only accurate to 2 or 3. They will accept significant figures. Times 10 to the minus 23. You can either use kilogram meters per second or Newton seconds. I prefer kilograms meters per second because it shows us the mass times the velocity. Don't forget to put the units in. Once we know the momentum, we can then use this value to put it into the equation for de Broglie, So all we want to do is we want to work out the wavelength. So we put in lambda. H is Planck's constant, which is 6.63 times 10 to the minus 34 joule seconds divided by 3.62 times 10 to the minus 23, and that will give you a value of 1.83 times 10 to the minus 11 meters. Now if you think about it, this is a very small wavelength. The size of an atom is 10 to the minus 10 meters. So you can see that it's smaller than an atom. So that's how you should lay out. I'm sorry about, didn't have everything in the question. This is where you need to make sure you got everything clearly marked out. So the method I've used, I would get 1 mark for using this equation but putting in the correct values. Yeah. I would get 1 mark for using this equation by putting in the correct values, and 1 mark for the answer. Again, don't forget the units. Okay. So I think we'll do at least 1 more question because we've come to 11-12 minutes now. The next question is magnetic fields. So I think I'm going to zoom out a little bit here. Okay. A student clamped a metal rod horizontally in a uniform magnetic field. So you can see the magnetic field. So it's the normal magnets you use in a physics lab. North and south poles will be opposite each other. Okay. The metal rod is this. So he's going to run a current through there. Student connected the ends of the metal rod to a power supply and an ammeter and a switch in a series circuit. So they haven't shown you the circuit, they're just telling you that there will be current either going one way or the other, doesn't really matter, but it will go the correct direction to give you the results that they're going to give you, so don't be influenced by the arrow I put on. When the student closed the circuit, there was a current in the metal rod. Okay, so that would be the current. Could be in the opposite direction. When the switch was closed, the reading on the balance, so reading on the balance is there, increased by 2.8 grams. The reading on the ammeter was 3.6 amps, so we've been given the I. They then tell us that the flux density of the magnetic field was 120 milliteslas. Yeah, and milli means 120 times 10 to the minus 3 teslas. Yeah, I still get A-level students asking me about prefixes. You need to make sure you know all the common prefixes. Okay, then use standard form when you're doing your calculations. The length of the rod in the magnetic field was L. So they're not talking about the length of the rod, but the length of the magnetic field in the magnetic field, because that's the only bit that matters. That's where the current interacts with the magnetic field. So it's the length of the magnets, in other words. They want us to calculate L. Well, this is F equals BIL. And there is sometimes a sine theta, but because they said the rod is horizontal, yeah, there it's at right angles, so sine theta equals 1. Okay, so they put a capital L, so I'm just going to change that to a capital L. And F is equal to the mass times gravity, which is the force that we get here, 2.8 grams. So first we could quickly do this, since we're on it. 2.8 times 10 to the minus 3 multiplied by 9.81 allows us to get a force in newtons. I'm just looking at the calculation I did earlier. The weight or the force that's acting due to the current going through comes out to 0.02747 newtons if you have it accurate. You may need that accurate value to get an accurate value for the length. So when you're doing it on your calculator, make sure you use the accurate value. So once you know the F, that's the F, we've been given the B, we've been given the I, the only thing you need to work out is the L. So you change the subject to the formula. L equals F divided by B and divided by I. So you put the values in, 0.02747 divided by 120 times 10 to the minus 3 Teslas, multiplied by the current, which is given here as 3.6 amps. And once you have those numbers in the calculator, you should get a length of 0.0636. Put that here, 0.0636. And I'm doing that on purpose. That will be in meters, because I'm going to round it up to two significant figures in the final answer to show that I know we really only have two significant figures, 3.6 amps, 120 milliteslas, 2.8 grams. All the data we're given is two significant figures, so the answer should be two significant figures. How do you get the marks? You probably get one for working out the weight, which is the force. You get one for using the BIL sine theta equation, so putting the numbers in, and then you get the third mark for the answer with the units. Okay, so I think I'm going to stop and this one, let's do one more. So we've got 17 minutes on this question. So question 14 is a car that's traveling in a circular path. Yeah. So again, we need to know the equations for circular motion. However, this is a description. You have to assess the claims made by the student or the passenger. So a car travels in a circular path as shown. It's viewed from above, so it's a horizontal path. So we don't have to worry about the forces changing. So when you're going in a circular motion, you know that the only force is centripetal force. So for a car, that could be the friction between the tires and the road. But then you read the question and it says, the passenger in the car made the following claim. When the car was travelling at high speed around the circular path, I was thrown outwards due to the force acting on me. Well, the outward force acting on me was the centrifugal force. Well, you should know immediately if they give you a question about centrifugal force, assess the claim made by the passenger. So you'll get 1 mark for just saying there is no such force as an outward or centrifugal force. Yeah? So you're assessing the claim. So automatically you probably would get 1 mark just by saying that, even if you can't explain it clearly. Okay? So how would you get the other marks? So there is no outward force. That would get you 1 mark. So what's really going on in the car? So obviously the car feels a force. That's why it goes in a circle. But the passenger is inside the car. And the passenger will feel that they want to well, from a Newton point of view, they'll feel that they want to travel in a straight line. So the first thing you need to make a point about is that although it feels like you're being thrown to the side of the car, or that Newton's first law needs to be mentioned. So you need to make a comment about Newton's first law. So the mark scheme actually puts it as such. Apply Newton's first law to the path of the passenger, for example. So if no force on the passenger, if there was no force towards the center on the passenger would move in a straight line, yeah, at constant velocity. This is not happening. We know that the passenger is moving with the car in a circle. So we know that really Newton's first law. So if there was no forces, the passenger would move in a straight line. Yeah? But you need to make sure you are wording it correctly. Now, the way you word it is the quality of the written communication you're going to get. So as long as you've clearly shown the examiner that you understand that Newton's first law is involved in your answer, you will get the Newton's first law mark. Okay? So you need to make sure you do that. But then you say, well, there must be a force acting. So the next one, you must say, well, there must be a force acting on the passenger. So when you're driving the car, what actually happens? Yeah? So you then have got to say, but there must be a force acting on the passenger, yeah, towards the center of the circle. And this will be, so for it to, obviously is going in a circle, so there must be a force acting on the passenger towards the center of the circle, and it must be inwards, yes? So that automatically shows that there is no such thing as an outward force. So as long as you know that this is now an unbalanced force situation, this is actually Newton's second law. There must be a force acting on it, yeah? And what provides that inward force acting on the passenger? This force is provided by the car on the passenger. Now, how that happens, yeah, it could be that if your car is going really fast around the circle, the person will feel pushed towards the door. Now, if it's in England, the driver's on the inside and the passenger's on this side of the car. So maybe that if the driver's going too fast around the circle, it may feel, because of Newton's first law, that the passenger will be pushed against the door, yes, or feels like it. And it's the door then is then the force that's helping to keep the passenger in the car and stops them from being flung out. Obviously, if there was no door, they may fall out of the car because of Newton's first law. So that's how you break down, yeah, the answer into 4 points. Okay? The force is provided by the car on the passenger. As long as you get those 4 points across, you'll be fine. So that's how you get the 4 points. And it's just a skill to change your physics understanding into a clear, logical reasoning in English. Okay? Well, thank you very much for watching the second video in this October 23 paper. Yeah? I will continue to answer these questions. So we've done up to question 14. I will continue to answer the following questions, but I'll do it in a following video. Okay? I like to keep my videos down to 20 minutes or shorter. Thank you very much for watching. Please share the video with your friends. Like it so we get more people watching it. and subscribe if you want to know when the next video is going to be ready. Thank you.